In my previous video I talked about these three HP3468A multimeters, and that I wasn't happy with the displays on them. That was one thing, but more immediately is that the calibration constants, which are stored in CMOS RAM backed up by a battery, will disappear if that battery fails, and also that the control firmware ROM is prone apparently to failure. So I want to look at trying to save the contents of the calibration RAM and the firmware ROMs. And if you watch when we turn it on, they all go through this self-test, which does a checksum of the ROM and the calibration RAM. So given that no errors were shown, those things are still intact. So I want to get them out while that remains true. I'll open them all up and we'll have a closer look inside. So there they are with the lids off. I've arbitrarily assigned numbers 2, 3 and 1 to them before I realised I should have done it in order of age, which is what these are now. This is the oldest one, made in about 1981. Number 3 was made in about 1991, and number 1 was made in 1993. And I've had this one open before, obviously. There's a shield over the sensitive analog part, so we'll look at this one first, since that's been removed. So the main parts, so there's the battery I was talking about, and I've stuck this battery on top foolishly before I realised I couldn't get the shield on if I did that. So that's why the shield's not there. There's the A to D converter. That little TO92 package there is the voltage reference. It's a Zener diode, 6.9 volts. Here's the processor. It's an 8039 from the Intel MCS48 series. That's the HPIL interface bus. It doesn't use GPIB, it uses a 3-wire in and out pair called HPIL. There's the firmware ROM that may lose its contents at any time, and there's the calibration RAM that stores the data with this battery to back it up when the power's not on. That's only for calibration data, that's not system RAM. There's 128 bytes of RAM inside the chip. That's where the stack and working storage is. So the only external memory to that for the processor to operate is this ROM. This unobtainium looking thing is a part of the analog input switching. It's got a bunch of FETs and switches and things inside of it. Some read relays, power supply. I should put something over that fuse because that's mains voltage there, so it's a bit nasty to have that just sitting there without anything to stop inadvertent touching. Now this ROM is 24 pins, and that might be the one that's bad. The other ones have, and it's got a strange pin out too. It's not like a 2716 or whatever the equivalent in that series with 24 pins is. Whereas the later two have 28-pin chips, and they have the same pin out as a 2764, and all these chips are 8K, by the way, 8K by 8. These calibration ROMs are only 256 bytes and only 4 bytes wide, so they just sit on the lowest 4 bits of the address data bus. So 256 by 4, and these are 8K by 8. So looking at my stretched out background image of the insides of unit number 2, my original plan to read out the values in the ROM and the RAM was to hook an Arduino onto this, probably onto all the pins on that guy, and drive the address and control signals and then read out what came out of the data pins, and likewise with this one. Trouble is that's not really possible because signals after drive would conflict with the normal source of those drive signals, and the only way around that would be to cut traces or something. So I didn't want to do that, and so instead of using the Arduino that way, I'm going to use a Atmel 1284 40-pin job, which I described in a previous video. And it's got a lot of internal memory, 16K, and 32 I/O pins, less 2 for UART, so 30 I/O pins, which is heaps. I'm going to wire that onto here, and instead of driving the chips, I'm going to make it act as a bus snipper.
So it'll just watch the activity on the bus, recording addresses and data, and because at startup this thing goes through a self-test, it will read every byte in that memory, so that every byte will appear on the data bus, and it does the same thing for the calibration RAM. Everything in that will appear on the data bus as well. And if I just record that stuff and upload it to a PC, I should be able to go through and extract the data that forms the ROM and the calibration RAM as well. That's called bus sniffing. The bus sniffer has to watch this thing in real time. It can't just, if it was driving it, it could do it at its leisure, but it's got to watch this thing in real time. So even though the AVR is running at 20 megahertz, using Arduino code in it would be way too slow. So it's got to be programmed in assembler and pretty tightly as well. This thing's considerably slower than the AVR. AVR should be able to keep up with what this thing's doing. So let's have a look at the circuit. And here's the relevant part of the schematic, which is the main digital section. You can see the processor there. There's the Control ROM, the Calibration RAM, and this here is an 8-bit latch, because this processor doesn't have an address bus. So to talk to the memories, it's got to present an address, and it does that by first putting the address out on the data bus and then setting this ALE signal, address latch enable, which makes this latch the 8 bits there, and then they're presented out here to the RAM and the ROM. And then they put their data out onto the data bus when enabled by the processor. For the ROM, the PSEN signal drives the chip enable signal on the ROM, so after it's latched the address and presented it here, it turns that signal on. After a short delay, the ROM will output its data to there, which will be instructions typically for the processor to run. For the calibration RAM, very similar, except it's the read signal from the processor goes to its output disable. That's active high, this is active low. So when that's low, the output disable is disabled. So the output is enabled. And if you see there, it's only 4 bits wide. The top 4 bits aren't used, but of course the Control ROM uses all 8 bits. The other chip enable for the RAM comes from reset, so that's high once the processor is running, and this is all the battery backup business, but that doesn't change once the processor is running. It needs a second chip enable signal, which comes from this other little latch, which comes from port 2, uses 4 bits from that. One of them goes here, the others go out here to the display. And that port also provides 4 more address lines into this. So we've got 8 here, plus 4 more there, and that will give us 4K addressing, but this is an 8K ROM, so it needs a 13th address bit, which comes from port 1 bit 4 into A12. That makes things difficult for trying to understand what's going on inside this ROM, but we won't discuss that in this video. This is how it was wired to the 18MB1284. Similar to the other diagram: processor, Control ROM, Calibration RAM, address latch, data bus, 8 of them, only 4 come out of the RAM. Those 8 bits go straight into the 18MB. The latched address, 8 bits, also goes into the 18MB, and the high byte of the address, another 8 bits, 4 of them come from that port 2, 0 to 3 there. The 13th one, port 1 bit 4, goes to PC4, and there's 3 unused. This thing records all 16 address bits, because I hope to make this general purpose, so I have a 6809 system, or a couple of them, that I might want to connect this to, so I'm allowing for the possibility of recording 16-bit addresses. On top of that, we've got 4 more control signals that we're also monitoring, and 1 output, which is going to the reset. So this thing can reset that processor in order to control what's going on, to control the recording. And 2 of these signals are used for triggering the recording. The PSEN, which drives the chip enable on the ROM, that's for recording activity regarding the ROM, so we can trigger on that signal. Or if we trigger on this one, which is the read signal that controls the calibration RAM, we can read out the RAM values. All the signals we need are on there except for just a few, and I've connected to pins onto all of those, header pins, all except pin 24. We don't need the power from that. Plus a few others, there's 4 or so on the processor, and one on this chip over here we have to grab, and a ground, and there's the digital ground there, so also soldered a pin to that. There's what it looks like with all the pins wired across to this thing. I've mounted taken the meter out of the case and bolted it onto this board using the 2 transformer screw holes, so that's nice and stable, and the ATmega 1284 that I'm using is on standoff, so it's all nice and stable. And there's the FTDI serial to USB converter going off to the PC. There's the ground wire. As you can see, most of the wires coming off the ROM. 1, 2, looks like only 3 coming off there, and 1 there. Close up, yeah, it's only 3 on the processor. There's the ground, and there's the other pin we need. You would think soldering gold plated pins onto gold plated pins would work rather nicely, but it didn't go so easily. Not as easily as I thought anyway. So that's how it's been wired up. So looking at the timing diagram for the 8039 processor, that address latch enable signal, on the falling edge the data bus has the address to be latched, so when that drops, there it is there, it latches the address that's on the data bus into this, and then that's available to the ROM and the RAM. A short time later, once the processor has taken the address off the data bus and turned it into inputs, the PSEN signal goes low, which is this guy, and it enables the ROM, and during this period there's the access time for the ROM, and finally there should be data coming out of the ROM, which will be the instructions. This is for instruction fetch. So there's the access time of the ROM, and when PSN goes high, the processor latches whatever's on the data bus, whatever's come out of the ROM. So it's got its instruction. And the RAM is very similar. ALE latches the address again, which goes out to the RAM, and the read signal, this guy, enables the RAM to output its data, and after its access time it should be sitting on the bus, and then on the rising edge the processor clocks in the data that the RAM put out. And we're watching all that here. We can see the addresses, we can see what's on the data bus, we can trigger on those signals so we know when that's happened. So looking at actual oscilloscope images of those signals, there's ALE and the PSEN signal, these two. The shapes are a bit different to the diagram, but we can see that the PSEN goes low for a microsecond, perhaps this time here, and for the reading from the RAM it's a little bit longer than a microsecond when the read signal goes low. Because we're watching the data bus, we can see all this data here, and we have latched the addresses here and here, and we've got the control signals to trigger on for this and this. So this thing can record a bunch of 4-byte samples, 1 byte of data bus, 2 bytes of address, and another byte of signals. That's one sample, and it's got 16K roughly of memory to store it in, so it can hold 4,000 samples. So there it is, all ready to go, with the Arduino powered on and the meter powered on. I have to turn this on first before I power on the meter, because if the meter's on first, the Arduino will try and power itself off the signals coming out of the meter, which can't be good for either of them. This way, when it's turned on, it won't do that, and since everything is an input to it, it's not providing any power into the meter when the meter's powered off. Let's have a quick look at the assembler program that I'm going to run on this. So here's my assembler, and looking at the definitions for the port pins, we can see port A, 7 bits are there for the data bus, port B, 8 bits for the low part of the address bus, port C, there's the other 8 bits, and 3 of them aren't used. Then port D is these signals here, including the 2 trigger signals and the reset signal for the processor, which is defined as an input, but when required it can turn it into an output, pulse it low to reset this processor, and then turn it back into an input again. Now the actual triggering and sampling of the signals, we'll have a look at that now. So here's the, ignore the ALE, we're just looking at this PSEN signal, the output enabled of the ROM, which is normally active high, which is inactive, and then goes active low for a short period to read from the ROM. So what the main loop of this thing is, this. It's in two phases. First it waits for the signal to be high to get in sync, so to make sure it's in this area. So there's a tight little loop there which is only 3 or 4 instruction cycles long, and at 20 megahertz that's 50 nanoseconds per cycle, so not very long before it realizes that this thing is high. And then once it's high it waits for it to go low. So we know we're in this part, and then we wait for this to happen, and when it does we know that the address is valid, so we pull in the 2 bytes of address data at this time, and then I don't think I've explained it earlier here, but we can make this thing wait until a certain address appears. So that's what this stuff here is about. It's checking whether or not the address is the one it wants, and if not it goes back up here and waits for the signal to go high again, and then waits for the next low and checks if that address is correct. More than that, as well as if it does get the right address, it also wants to see that address appear a certain number of times. It decrements a counter, and if it hasn't got back to down to zero yet, it hasn't seen that address enough times. So again, it waits for the signal to go high and then waits for the next low up there. But if we did have the right address and it was executed the number of times we want, then it sets this active bit, goes up here and waits for it to go high again, and then when it's gone high it falls through to here. That active bit is now set and it goes into phase 2, which is the actual recording. So this was phase A, was to just wait for the correct address to appear the correct number of times. When it has happened, it'll do this jump here to phase B, where again it waits for the high to appear, and it will be because that's how it got here. It jumped to phase B when the signal was high, and now it waits for the signal to go low. Reads in the address and the signals on port D, but not the data. They're all valid at this time, but the data isn't valid till the access time of the memories happen. In here we can insert a few delays. There's that tight little loop there, DEC and BRNE, which takes 3 cycles, so 150 nanoseconds per loop, so we can add in increments of 150 nanoseconds before we then finally read in the data. So it's been waiting for that to go low. When it does, it reads in the address and the control signals, but waits a certain amount of time until it reads in the data. So now it's got all 4 bytes that it needs for the sample. It stores them away in the buffer and waits for the signal to return back to high again. When it has, it decrements how many samples it's done, because it can only hold 4,000, and if it hasn't reached that yet, then it loops up and goes through this again until it's done 4,000 samples and sets the complete flag. I'll just show you a little bit more. There's a whole bunch of commands it can take. R starts the recording, kicks off the process I just described. S does the same thing, but it doesn't reset the processor in the meter before it starts. 2 tells it to trigger on the other trigger signal, the one for the RAM, the calibration RAM, but normally by default it triggers on the ROM signal. This is where we tell it that address that it has to wait for, and this tells it how many counts of that address before recording. Once we've done the recording, we can press D, which will dump it. We can display the operating parameters set up by all this stuff, and we can reset them to standard. The address in this thing is only 13 bits, so we can apply a mask to the address before it tests it. so we want 1F in there, so that knocks off the top 3 bits, which we're not interested in, although they should be 0, but in case there's any noise we just mask them off. This E tells it how many of those 150 nanosecond delays to insert for access time. So now we'll download it. Looks like an Arduino when it's downloading, and then it switches automatically to the terminal. I'm not quite sure we didn't see the startup messages, but if I just put in P to show the operating parameters, there we are. It's triggering on signal 01. The activation address is 0, which means it doesn't wait for any particular address. Same for the activation count, doesn't require a certain number of them. The address mask is FF. Well, we normally want 1F, so we can go M1F, and it's changed it to M1F. Access delay is 2 of those loops, and we can control how much data it dumps. I'll show you that in a second. If I press R, it'll do a recording, which is very quick, 4,000 samples, and then D dumps the data. You can see a few glitches in there. That's just the terminal playing up. Got a few bugs in it. And what have we got here? This is simply a counter. There's the 8 bits of signal information. There's the 16 bits of address, and there's what's on the data bus at that time. So that's just a quick look at the assembler program. Although you can drive it manually, you wouldn't use it for much. Although we can clear all the parameters. If I set the trigger to 2 for the calibration RAM, and then do a R. See how that took a bit longer? Because it has to wait for the calibration RAM signal. Doesn't happen anywhere near as often, and it only happens at startup. So, but that's enough to grab the sample data for the calibration RAM, and we only need one run to do that. We don't have to restart at another address. And we dump that. If you look in this area, all those Fs, that's because we're only reading 4 bits out of the calibration RAM. The high 4 bits are always a 1, so the actual data is just a low nibble after the F. And we know when we're reading the calibration RAM because of the signals encoded in that 4th byte. Now, we didn't have to use the terminal program that's built into this assembler. We can use Arduino as well, but I'll just show you one other thing. The baud rate divisor. Dumping 4,000 samples or 16,000 bytes gets pretty tedious. So at 57,600 baud, if you work out the baud rate divisor, it has to be 20.7, but it's an integer. If you want it to be very accurate, it should be a complete integer. At 57,600, it's slow enough that drifts in timing don't matter too much. But if you try and go to say 115, 200, it's too far. But fortunately, at 250 kilobaud, the baud rate divisor is a precise integer, 4, and it's fast. So that's what I'm using here. And when I first did this, some operations took an hour, and now they're only 5 minutes. Now, you don't have to use that, as I said. You can use Arduino. So you can fire up or any terminal emulator. And there we see the startup message, which we didn't see in the other thing. I don't know why. It's already set to 250 kilobaud. So if I just do a recording there, you've got to go up here on this thing, record, and away it goes. Samples are done, and then D for dump, and there's the data again. Although you can run it through a terminal emulator, it's very tedious. So we'll get rid of that. So I've written a program to automate all of this. Trace recorder and analyzer, so we can connect to the Arduino and do various things. We can select either the ROM or the RAM to be recorded. We'll do the ROM, and I want it to start and reset, and I want it to repeat. This is where the activation address and activation count come in. Run trace, and it's set the mask to 1F, and there it did 1 sample, dumped it, and notice how it said the last entry was that address, and this is the use count, how many times that address was used. So it then sticks those values into here for the next run. So the next run waits until that address has been hit that many times. So in effect, each sample block waits for the point where the previous one left off and then starts recording from there. So here's what it looks like at this end of things. I'll run the ROM trace from the beginning and it resets the thing, and you'll see over here twinkles a couple of times when it sends the command, and now it's dumping the data. Twinkle, next sample block, dumping data. Twinkle is sending the commands again, and so on. And each time this thing resets, goes through its power on self-test until this has recorded its 4,000 samples, and then it starts again. But each time it waits a little bit further into the sequence before it starts recording, so it'll gradually get slightly slower. And I've actually run this thing to collect 2 million samples. That took about 18 minutes, which is not bad. So that's what it looks like when it's running. I found that to get all the images, all the bytes in the ROM, I need to collect 328,000 samples, but let's just stop it at 44,000 for now. We'll just finish this run. Done. If we go to record data, it shows what it's read, and it's done a bit of analysis and reformatting. It's inserted these blank lines wherever the address changes, so there's been a transfer of control to a different part of the program, so that helps delineate transfers of control. It also has interpreted those 4 control signals in the signals byte, low, high, and we've also got a couple of extra fields here. If I go to around about line 4000, there's a asterisk there at 4000. That means that was the end of one sample block, and this is the start of the next one. But also there's 2 bits in this data byte, this signals byte, that up the top that aren't used, so it sets the topmost, the leftmost one, 8 to 0, to indicate that that's happened. Another interesting thing that you might want to look at is, for example here, you see here we've got an N, and again we're using one of those 2 unused bits, the 40 bit, to indicate the N as well. That is a non-instruction reference to the ROM. If you look here, it was executing an instruction at 13FE, and then the address is different, but it didn't interpret that as a change of a transfer of control, because immediately after that it returns to the address following the first one. It didn't transfer control at all. That's just a memory read from the ROM, but not for an instruction. So in fact this is part of the checksum routine. It's reading a byte out of the ROM, and then there'll be another one down here, different address in ROM, and it's a different part of the program. Actually, it's funny how this thing works. It's a separate routine. There are many routines for reading bytes out of the ROM. It's a bit of a dog's breakfast, but that's because of the architecture of this 8039 thing. Also, this is actually a subroutine called read from memory. There's a memory read, and then it does a return. Now there was an extra dummy cycle appearing after a return from subroutine, so that for some reason, I don't know why, it's just a quirk of the processor, it does another read on a return. That's just been discarded because it contains no useful information. This thing can also load a reference image of a ROM. You see that equal sign there, that indicates the data on the bus at that address matches what's in that reference image of the ROM, and it works until about here, and then it stops. That's because this version of the ROM that we're reading here is an old version, and I'm comparing it to a later version of the ROM that I found on the web. If I change the reference ROM image for this ROM image, there'd be equal signs everywhere. So anyway, we can look at the ROM image, and there's all these zeros. That's because we didn't let the thing run long enough to read every part of the ROM. So there's a whole lot of empty spaces, but there's where there is non-zeros, that's where it worked. And this is a checksum routine working. It works in a strange way, especially in the top half of the memory. This is all just checksum reads. We won't go into that too much. With the calibration RAM, go back, select RAM this time, and tell it to run a trace, but from reset, but no repeating. And done. And if we look here, It's asking me if I want to save all this stuff, if I've let the recording run to completion. I didn't let the other one run. This one was complete. We'll say don't worry about that. It'll stick that information in a file when it saves it. Now here is the Calibration Ram Accesses. This is the address from 00 to FF. There's only 256 of them, and this is what was on the data bus when it read from that calibration RAM. And in fact, it never read those locations there, and it never does. It reads each of these once. Some of them, these 16 here, it reads twice, but the data is the same both times. Then more single accesses, then no accesses until the very last byte, which it accesses twice, and then it puts that in a table. So that's the contents of the calibration RAM. Oh, there we have it. With what I know now, I could rewrite that assembler program, this thing, or write another version of it, that instead of creating a trace file, just looks for all the accesses to the ROM and the calibration RAM, and when it's found every address has been hit, then it could just upload purely the ROM data without all this trace information. And I may yet do that because that would probably be handy, because I've got 2 more of these meters to do it on, so why not? But the information that this generates, all that trace data, is still very valuable. This trace information, which shows exactly what instructions are being executed, is a huge help in understanding what that ROM is doing. I'll show you a quick look at the disassembler. Right, here's my disassembler program. Now, there's a lot to show in this, and it would take a significant video just by itself, so I'm not going to go too far into it. I'm just going to briefly show you what's going on and how the trace file and the ROM image created by the other stuff is useful. So there's the ROM image that we created just before, and here's the output. Now, I've done quite a bit of editing trying to unravel what's going on in here, and I'm only a short way into it. So you can see most sections don't have any comments because I don't know what the hell they do. And then we see I've made a few comments. Some sections I've been able to unravel to some degree. I'm trying to find the checksum bit. Here's how it checksums the high half of the ROM, which is completely different to how it checksums the low half of the ROM, but anyway. Let's find something interesting. There's some error messages, or some text. Some more of that somewhere else. The rest of it. Yeah, there. Some more messages. There's the trace information, and this one has 2 million samples. And we can do things, and I can take this output and I'll make it float so that we can see 2 screens at once. Go back to that trace stuff and click there, and there it is in the trace. So I can just by pressing the down arrow step through the code. Now you see in here these little asterisks, asteri, they indicate where code that was found in the trace table, so that's known to be executed. For instance, there doesn't get executed. Look at the reset vector, which actually starts in the top half of ROM at 1000. There. See, that gets executed, jumps to main reset, which is down here, no, down there, starts executing stuff, jumps to go memory test. Let's go to there, shows us in the trace, but we can also the memory test, blah blah blah. So, and then we can also look at a map of the ROM. This is how it's categorized the areas that it found. There's one block there for each byte. There's 8,192 of them, and these colour codes indicate what it's for, but we can also look at what we found in the trace, and these are all the areas that were actually executed. Colours don't mean too much at the moment, so we'll make it black and white, and that's for the full trace, and we can determine how much of the trace we look at. So you can see it slowly do more and more of it. Now we've got a bug here. Now we've got a bug that should have shown only the data reads, and there's something wrong there. I won't try and fix that now. That was a really quick look. There's a lot to go on, and there's still a lot of bugs in there because it used to work better, and then I fixed it. And I've been struggling for days trying to get to where I was. And I've been going around in circles, and I'm still not where I was. So that'll have to do, I think. This video has gone on for way too long. Hope you found it enjoyable, interesting. Please give it a like if you did enjoy it, and I'll catch you later.